Okay, the cumulant generating function, which is closely related to the moment generating function. The cumulating generating function is something that second years see, and it might be mentioned in passing in maybe the help sessions in the first year stats course. Okay, why do we need to know about? We don't know about an MGF. We can use the MGF to churn out moments. Well, under certain conditions, this cumulant generating function you can use it to obtain the moments faster, as in the mean and the variance. So when I say moments, I'm specifically interested in the mean and variance. So let's define what it is first. Cumulating generating function, let's call it K, is a function of t, which is basically it's the log of the MGF. So I've got MGF, I take a log of it, that is the cumulative, the cumulant generating function, and that's all it is. So it's got to be, something more to it than that for its existence. So let me show it here. The case of a Poisson, let x be Poisson parameter lambda. Then I've proven today on the YouTube video, MGF for this is e to the lambda e to the t minus 1. Now, as I've shown on my video, that I can obtain the first moment and the second moment, and hence the variance, by differentiating this thing first time and setting t to 0 to get the first moment, and finding second derivative, setting t to 0 to get the second moment, ex squared. Alright, and but to do that I need to differentiate this guy here. Differentiate this guy here is actually not too hard because we did it by using the chain rule, but with the cumulating function, you can see if I take a log of this, I've got that log of this thing, that exponential disappears immediately. So therefore kt here is simply just lambda e to t minus 1. So that's why sometimes I said that this is actually a faster way to get the moments, because if you've got something starting with an exponential, take a log of it, it's gone. Alright. Now the result is this. This is the properties of the cumulative generating function. The property that we need is that expected value of x is the first derivative of the accumulating function evaluated at t0, and the variance of x is just the second derivative at 0. Now it's this variance I'm looking at, because this is why when it works it's quicker, because if you're using the MGF you have to differentiate it twice, alright, and then you've got to subtract the squared of the exponential of expectation of x, to get the variance. But this is just saying if you differentiate twice at t to 0 you've got it immediately. So let's try that. So in our example here with the Poisson, we have the expected value of x is equal to the first derivative of this guy with respect to t, and well, you can see immediately that's going to be lambda e to the t, and it should be evaluated at 0. So let me not even write that down. So let's say k, first derivative, let's make that clear, is equal to this guy, and just say therefore the expected value of x, which is equal to the first derivative of that cumulant generating function evaluated at t is 0, is equal to lambda. Done. And let's get the second derivative of this guy. Do it again. Well, that's just lambda e to the t. Therefore we can say that the variance of x is equal to second derivative of this cumulant CGF, let's say CGF evaluated at t is 0, and that's just going to be lambda again. Finished. End of video. Okay, so the CGF is just simply the log of the MGF, and the two properties that we're keen about it is that if we take the first derivative of this CGF and the value at t is 0, that gives us the mean. But if we take the second derivative and the value at t is 0, that gives us the variance straight away. Okay, and we just said that then this is pretty useful if our MGF has anything that's starting off with a log like this, exponential like this. Sorry. Okay, so hopefully that will come use someday.